So in the last video, we looked at the chain rule, which was a combination of two functions, one within the other. The product rule is different, but it might look the same. But it's two functions that we know how to take the derivative, multiply with each other, right? So f of x times g of x. Whereas when we looked at the chain rule, it was f of g of x, where g of x was within the function f of x. This time we're just multiplying the two functions. Now the rule says that if you have the product of these, when you want to take the derivative of this, we take the derivative of one of the functions and multiply by the other function, right? So f prime x multiplied by g of x. We add that to the derivative of the other function. So here we took the derivative of f of x, here we take the derivative of g of x, and then that one multiplied by f of x. So f prime times g plus f times g prime. So we'll take a look at a couple examples to make sure we understand this concept. So let's start with an example that we know the derivative of, right? We know the derivative of x cubed because that's just using the polynomial rule. That would be 3x squared. That's the derivative. But I can break this up into two parts. I can break it up and say x times x squared and just look at it as two functions. So if we look at it from this perspective, then we can call g of x my x term and x squared my function f term, right? And then we can apply the product rule like we see here. So graphically, x cubed is shown in red here. Then we have our two components, x squared and x multiplied together to give us the x cubed. All right, so the next thing we're going to do is take the derivative of both g and f. So the derivative of x is just 1, the derivative of x squared is 2x. We see that from the polynomial rule. All right, so now we just build our derivative using this formula. So f prime times g. F prime is 2x, g is x. And then f times gx. F is x squared, and g is 1. So they're 2x times x, 2x times x, and x squared times 1. And so we get our 3x squared, which we expect, right? The derivative of the polynomial x cubed is just 3x, 3 minus 1, or 3 times x squared. Right? So we can graph each of these components. Here in red dashed line is my 3x squared derivative, the full derivative, and then we have each individual combination derivative, right? This term and this term as 2x squared and x squared, 2x squared and x squared. And we've looked at this in a previous series of how changing the coefficient in front of x squared, the quadratic, tightens this graph as we see it changing from x squared, 2x squared, and then 3x squared. And just graphing the original function x cubed here, solid red line, and the dashed red line, we can see that this derivative does make sense, right? We have starting at a very large positive slope to a zero slope, right? Dashed line representing the derivative, and then a large, increasingly larger positive slope as well. Here's another example, e to the power 2x. So how do we change this to make it look like a product rule application? Well, we can break this up into e to the power x times e to the power x, right? Same thing. And you might look at this and say, oh, I could use the chain rule for here, for this problem. And you can, and we'll show you that we'll get the same answer in both cases using two different methods. But let's break this up into e to the x times e to the x. So g of x is going to be e to the x, f of x will also be e to the x. And multiplying g of x and f of x will give me my function y. So if I graph it, since g and f are the same, that's shown as a single graph, a single curve in green here. And then e to 2x, we can see that we have a sharper curve here. So we would expect the derivative of e to 2x to be steeper in this section than this one, right? Which would be larger than this one. After the y-axis, or basically when x is positive, right? So that's what we qualitatively can see, and let's see if we get that. So the next thing to do is take the derivative of each of these individually, which will just give us each of x. We can see that by the definition of the derivative of each of x that we solved for in the previous video. Then we plug into f prime g, f prime times g, each of x times each of x, plus f times g prime, f times g prime will be each of x times each of x. So what do we get? We get e to the power 2x plus e to the power 2x again. So 2 times e to the power 2x. And in the dash red line is my total derivative. And in the dash green line, we see e to the 2x. So 2 times that, obviously it's going to be offset and larger than. And if we combine e to the 2x and 2 times e to the 2x, we can see the graph. But actually, yeah, I forgot. We're going to use a chain rule to solve this one as well. So the chain rule is basically u substitution, right? So I can look at my function, each of x shows up here, but that's my outer function. That would be my f of x. My inner function, my g of x term would be 2x, or I can call that my u substitution. So I'll call u 2x. Then I can look at this as dy dx is equal to dy du times du dx, where u is equal to 2x. So dy du would be e to the power u du, right? So it's essentially this function here. So we get e to the power u times du dx. Du dx would be d2x dx, which would just be 2. And then we substitute 2x back for u in this eu function term. And we get 2 times e to the 2x, which we see here, right? So here we have the original function, e to the 2x. And here in the dashed line, we have the function 2 times e to the 2x, right? So we can see that the e to the 2x is going to have a steeper derivative, and it's reflected than e to the x, and it's reflected by each of these graphs. Okay, so here's just another example with 2x times cosine x. So we can group them either way. We can group 2x together, or we can group 2 times cosine x and x, right? Separate it any way we want. The constant actually is, it doesn't really matter, but I'm going to choose to do 2x and cosine x, right? So we can graph these, and I think we've seen a function like this in something similar as the final solution in one of the other videos, right? So in green right there, there's my cosine x oscillation. My 2x with this multiplication basically is the bounds for the amplitude of the full function 2x cosine x. And that makes sense because the 2x is the amplitude term in front of the trig function. So if I graph negative 2x, you would see the other side of the bounds here. You may notice if you add a trig function to another, like it goes 2x plus cosine x, you would see the oscillation of cosine x walking up the whatever curve you added it to, because it's that offset that's constantly changing, right? Okay, so again, focusing on the product rule here, we could take the derivative of each of these, 2x and cosine x. And derivative of 2x is just 2, right? We know that from the polynomial rule and the constant multiplication, right? So it's 2 times derivative of x, which is just 1. And then derivative of cosine x is just negative sine x, right? So then we plug it into this formula. F prime is negative sine x times g of x, which is just 2x, plus f of x, which is cosine x, times g prime x, which is just 2, right? So there's my f prime, there's my g, there's my f, and there's my g prime. If we expand it, we get negative 2x sine x plus 2 cosine x. And here we have the graphs for, where is this? 2x sine x in blue, 2 cosine x in green, and x sine, so this total sum in red, right? And if we graph both the final form and the original function, we see the relationship here. So it'd be easiest to look at the peaks and the 0 points to at least recognize initial points, right? So the saw line is my original function. So I got peak right there, lined up with the 0. I have a min here, lined up with the 0. I have positive slope after that, shown here. That's shown right there. Over here, I have a negative slope showing up here, and that's showing up right there. So at least from that perspective, it's consistent. And you can see the amplitude increasing for the derivative piece, which means the rate of change is changing. And you can see from the original graph that the amplitudes are also increasing, and so the rate of change will be increasing. So that piece of things is also consistent with expectations. Okay, so for our last example, we have x times natural log of x. We're always looking for the components within a function that we know the derivatives of, right? As we can see here. So this one's pretty straightforward. We have x as one function and natural log x as a second function. So to break it up in this way, and so we have x in blue here, and then we have natural log of x in green, and then we have the product of those two shown here. And we can use this to our advantage because we do know the derivatives of each of these individually. So when we get our final solution, we can see things like out here, we would expect the rate of change, or the derivative component of the full function, should be larger than 1, right? Larger than the derivative of this component. We would expect the derivative in this component to be negative, and then the derivative of this component should start being positive on the right. So we expect a 0 point somewhere around here. So let's see what if we actually see that in the final derivative. So the next step in the product rule is to take each of these sub-functions and take the derivative of those individually. Derivative of x is just x. Derivative of natural log x is 1 over x. So then we'll use these and apply it to this rule, right? So f prime gx would be 1 over x times x. F times g prime will be natural log x times 1. And that's what we show here, right? The two terms. And then we'll clean up. We'll have one function that's 1 and one product sum that's natural log x. So my final solution is 1 plus natural log x. So in blue here, we have the constant 1. And then in green, we have the natural log x. And then we have the offset of that with 1 plus natural log x, as shown here as my final derivative. So let's combine the original and final derivative forms to see what this looks like to make sure we get the results we expect, right? So we have there's our function right there. We said earlier that the derivative starts increasing past 1 around here. And so this is my dash. The dash curve is my full derivative, the 1 plus natural log x. So it's slowly increasing, but it's not constant, and it's definitely above 1. We see in this section here the derivative is negative, as is consistent with what visually we see in this section here. We see some kind of minimum occurring here, which is represented by crossing the x-axis for the derivative to be 0 at this point here, and then positive all the way out here, which is shown here. And like I said, we mentioned earlier that it's above 1, right? So you see the application of both the chain rule from the previous video and the product rule here is quite straightforward. Once you identify what the sub-function components are, the last tool that we'll learn is the quotient rule, and we'll use it in a very similar way that we set up the product rule here.